Good morning. In this lecture, we will introduce a new type of device. It's called the Operational Amplifier and is abbreviated as Op-Amp. Operational Amplifier is a circuit that can perform the mathematical operations like addition, subtraction, integration, differentiation, etc. The important feature of this operational amplifier is that it amplifies the difference in the voltages applied at the two input terminals. Not the voltage as such applied to the input terminal is not amplified, but the difference in the voltages applied to the two input terminals is amplified in the case of an operational amplifier. And we can use this feature of the operational amplifier for the purpose of mathematical operations like addition, subtraction, integration, differentiation, etc. Here this diagram represents a block diagram of operational amplifier. Actually, an operational amplifier consisting of three stages: an input stage, an intermediate common emitter transistor amplifier stage, and an output stage. So the input stage of an operational amplifier is a differential amplifier. The differential amplifier is a particular type of amplifier which amplifies the difference in the input voltages applied to that amplifier or that circuit. And this difference in amplifier is followed with a series of multi-stages of common emitter transistor amplifier, which provides very high gain of the difference in the voltages applied to the input of this op-amp, and which is the second stage of an operational amplifier. And the final stage, that is the output stage, which is actually a class B push-pull emitter follower. Emitter follower is a circuit that does not give any voltage gain, but it provides a certain current gain. The importance of this emitter follower is that it has very low output impedance. Ideally speaking, the output impedance of an emitter follower is 0. So these three circuits, a differential amplifier and a series of multi-stages of common emitter transistor amplifier and a class B push-pull emitter follower, constitute an operational amplifier. In the case of a common emitter transistor amplifier, actually it is a multi-stage, or it is having a series of stages, and these stages are directly coupled so that both AC and DC voltages are amplified in the case of a common emitter amplifier stages of an operational amplifier. Now, typically speaking, the input impedance is very high. That ideally speaking, it is taken to be infinite. That is one of the important feature of an operational amplifier. The input impedance is very high, or it is infinite. Due to this reason, the current drawn from the source by the circuit or the op-amp is 0. And regarding the output impedance of the amplifier, operational amplifier, the output impedance is very low. In practical cases, it is less than 200 ohms, and ideally we take it as 0 itself. So the input-output impedance of an operational amplifier is ideally 0. So we can say that for an ideal op-amp, operational amplifier, the input impedance is infinite, the output impedance is zero. For practical cases, our input impedance is very high, so that it does not draw any current from the voltage source, and output impedance is very low, it is less than 200 ohms. The importance of having this output impedance is very low is that it provides almost constant output voltage irrespective of the current drawn by the load from the circuit. And if you consider the voltage gain, especially the open loop gain, this term which we are already discussed while discussing the feedback amplifiers. When there is a feedback in an amplifier, this amplifier circuit and feedback circuit forms a closed loop. So the gain of an amplifier with feedback is called the closed loop gain, and the gain of an amplifier without a feedback is called an open loop gain. So if we consider the open loop gain of an op-amp, it is very high. For ideal cases, we are taking it to be infinite. For practical cases, the open loop gain is usually greater than 10 raised to 5, that is greater than 10,000. So another thing is that this open loop gain of an operational amplifier is very high. In order to achieve the greater bandwidth and greater stability, we should use negative feedback in the case of an operational amplifier. So almost always an operational amplifier is operated with a negative feedback because it is having a very high open loop gain. So we will sacrifice our gain to achieve the advantages of negative feedback, including the large bandwidth and greater gain stability. So these are the different characteristics of an op-amp, operational amplifier. So an operational amplifier is a circuit that can perform the different mathematical operations like addition, subtraction, integration and differentiation. An operational amplifier usually consisting of 3 stages. The input stage is a differential amplifier, and it is followed by a series of multi-stage common emitter transistor amplifier which provides very high gain, and the last stage, which is the output stage, which is a class B push-pull emitter follower. Now if we consider the entire operational amplifier, the different characteristics of a different operational amplifier are: it amplifies the difference in the voltages applied at the 2 input terminals of the amplifier. And for an ideal op-amp, we can say that the input impedance is infinite and output impedance is ideally it is 0. The open loop gain, which is denoted as AOL, A represents the voltage gain and OL represents the open loop gain. The open loop gain of an ideal op-amp is also infinite. So these are the 3 important things in the case of an ideal op-amp, and usually an operational amplifier is operated with a negative feedback in order to get the stability and gain stability and better bandwidth. Another quantity which is of great importance in the case of operational amplifier is the CMRR, which is called the common mode rejection ratio. It is also very high, which is usually greater than 90 decibel. The common mode rejection ratio is the ratio of the gain of the differential mode to the gain of the common mode. The differential mode means the gain of the amplifier when it is operated in the differential mode, that is the two inputs are having a certain difference, and the gain of an amplifier when two input voltages are different is called ADM or differential mode. And ACM is the common mode, which means that the gain of the amplifier when the two input voltages are the same, that is the voltages applied to the two input terminals are same, then the corresponding gain of the amplifier is called represented by ACM, the gain of the amplifier in common mode. So the ratio of the differential mode to the common mode is called CMRR, common mode rejection ratio, which is very high in the case of an operational amplifier. So these are the some of the characteristics of features of an operational amplifier. Now let's see the schematic symbol of an operational amplifier. An operational amplifier actually consisting of two input terminals, which are named as inverting input terminal and a non-inverting input terminal. They are represented by plus and minus. Plus represents the non-inverting input terminal and minus represents the inverting input terminal. Here the non-inverting and inverting actually represents when a signal is applied to this non-inverting terminal, the output will be in phase with the input voltage, and when a voltage is applied to the inverting input terminal, there will be a 180-degree phase difference between the output voltage and the applied input voltage. So that's why these two terminals are named as inverting input terminal and non-inverting input terminal. So non-inverting input terminal means the output voltage will be in phase with the voltage applied to this terminal. Now if we consider the inverting terminal, these non-inverting and inverting terminals are the two input terminals of an operational amplifier, of which if a voltage is applied to the inverting terminal, then the output voltage will be out of phase, or there is a phase difference of 180-degree between the input and output voltages. That is, the output voltage will be out of phase with the voltage applied to this terminal. So that is the two terminals of two input terminals of an operational amplifier. Then there is an output terminal which is from which we are taking the output voltage, and two other terminals where here we are represented as plus V and minus V, where plus V is 15 volt and minus V is minus 15 volt, which are the terminals for supply voltages. So here we are applying the DC supply voltages. So these are the 5 terminals of a operational amplifier. 2 more terminals are there which are not represented in the schematic symbol of an op amp, but they are the offset null terminals. These terminals are used when there is an output voltage even when the two input voltages are the same. Usually an operational amplifier amplifies the difference in the two voltages, input voltages. If the two input voltages are the same, then a perfect operational amplifier will not give any output voltage. In certain cases, if there is output voltage even when the two input voltages are same, then we have to apply a proper voltages to the two terminals named as offset null terminals in order to make the output voltage 0. So there is a plus offset null terminal and a minus offset null terminal in an operational amplifier. So that is the different terminals of an operational amplifier. And here usually in circuits we will use the figure which is on the right side of this one. Here we will not represent the terminals for the power supply when we are using an op amp in a circuit. So the 3 terminals which are used in the schematic symbol of an operational amplifier are the 2 input terminals and 1 output terminal. So the 2 input terminals are the inverting input terminal which is represented by the negative sign, and non-inverting input terminal which is represented by the positive terminal and the output. So this is the actual schematic symbol of an operational amplifier. Now let's consider about the output voltages of an operational amplifier, or output voltage from an operational amplifier. Actually, the output voltage from an operational amplifier depends on 3 factors. One is the voltage gain of the operational amplifier, the A, which may be open loop gain or which may be closed loop gain. Then second one is the polarity relationship between the input voltages, and the third one is the values of supply voltages. So to discuss it, let's consider an operational amplifier. Suppose this is an inverting terminal and this is the non-inverting terminal and this is the output terminal. This is the now the maximum possible gain from an given operational amplifier is called open loop gain. So open loop gain is the maximum possible gain from an operational amplifier, which is obtained when there is no feedback. When a feedback is applied, that is a part of the output signal is sent back to the input terminal. Usually it is negative feedback is employed. So we will have a feedback resistance connected from the output terminal to the inverting input terminal. Then the output and input will be the feedback voltage will be out of phase or 180 degree out of phase, so that again will be reduced, which is called closed loop gain SCL. So voltage gain of an operational amplifier actually determines the output voltage from an op amp. That is, if there is no feedback, the output voltage will be maximum, and when a feedback is applied, then the output voltage will be reduced. Where the gain of the operational amplifier without feedback, which provides the maximum possible voltage gain, is called open loop gain. And when the feedback is applied, the voltage gain of the amplifier when feedback is applied is called closed loop gain. Now if we consider the polarity relation between the input voltages, suppose V1 is the voltage applied to the non-inverting terminal and V2 be the voltage applied to the non-inverting terminal, then the actual input voltage to the operational amplifier will be the difference in the two voltages which is amplified by the operational amplifier. So if you consider V1 minus V2, which is actually the input voltage. So if this V1 minus V2 is positive, the output voltage will be also positive. Means that the input voltage and output voltages are in phase. When this V in, that is the difference in V1 minus V2 is negative, then the output voltage will be negative. That means that the output voltage and input voltages are out of phase. So the polarity relationship between the input voltages, that is V in, actually determines the output polarity of the output voltage. The magnitude of the output voltage is actually determined by the gain of the operational amplifier. If there is no feedback, it is determined by the open loop gain, and if there is a feedback, it is determined by the closed loop gain. That we will discuss while discussing different op amp circuits. What is the closed loop gain for different amplifiers? Now the polarity of the output voltage is determined by the polarity relation between the input voltages. If the difference in the input voltages, that is V1 minus V2, difference in the voltage at the non-inverting terminal and inverting terminal is positive, then the output voltage will also be positive. If the input voltage is negative, that is difference in the two input voltages are negative, then the output voltage will be negative. You should be taken care that always take V1 minus V2, where V1 is the voltage at the non-inverting input terminal and V2 is the voltage at the inverting input terminal. Now the third one is the value of the supply voltages. That is, we have to provide some supply voltages plus V and minus V to an operational amplifier. The value of this supply voltages will also determine the output voltage. So that's all about the output voltages of an operational amplifier. In the practical circuits, we will use, especially in our labs, we will use the IC741 as the operational amplifier. So the op amp which we are going to do in our practicals is using IC741, which is an operational amplifier. If you consider the pin diagram of an operational amplifier, this IC will have 8 pins. Usually you know that an operational amplifier will have 2 input pins, 1 output pin, 2 supply voltages, two pins for supply voltages and 2 pins for offset null voltages. So here we can have 8 pins, the IC741. So this is the pin diagram for IC741. This is the pin number, let it be 1, 2, 3, 4, 5, 6, 7, 8. Here this pin number 2 is the inverting input terminal. Pin number 3 is the non-inverting input terminal. And pin number 4 is the minus V, that is negative supply voltage. Pin number 6 is the output voltage. So, and pin number 7 is the positive supply voltage, that is plus V, that is positive supply voltage. These things are useful for your practicals. And here we are represented 5 pins, 3 more pins are there, one pin number 5 and pin number 8. This pin number 1 and 5 are used for the offset null voltages. So the offset null pins are 1 and 5, and the pin number 8 is having no connection. For the symmetry, it is provided here. So these are the different pins and is used in the IC741. So remember that for practical classes we are using IC741, and it is a 8-pin IC, and here it is an operational amplifier. It is having 8 pins. The pin 2 is the inverting input terminal. Whatever the voltage applied to the terminal 2 will be amplified and obtained across the output terminal 6, but it is there is a phase difference of 180 degree between the applied signal and the output voltage. Pin number 3 is the non-inverting input terminal. So it is also the input terminal, non-inverting input terminal. The 4 and 7 are the terminals used to give supply voltages, and 6 is the output terminal, and pin number 1 and 5 are used for offset null voltages. That's all about the basics of operational amplifier. Now we will discuss the application of operational amplifier, that will be discussed in the next video. Thank you.